Okay, related rates. Let's review real quick. Let's review the process, right? And then I just want to go through some more problems. Just takes a while, just getting used to going through these problems and setting them up. So related rates problems, these are problems where we're trying to relate rates of change in some situation, right? What are the steps? So first step is where we're going to identify the video frame values, right? So we've got some specific frame in this video that the question is asking about, and we want to write down all the information we know about that one specific instant, that one frame in the video. It's going to include what we're given, what we're able to calculate in some cases, and what we're trying to find. And this is where we'd want to somehow try to come up with maybe like a picture, if that's appropriate, that relates the variables. So we have something visually, some way to kind of see how they're related. Okay, once we do that, then we're going to ignore all the dots, and we're going to try to come up with some static parent equation that relates the variables from step one. If we can come up with that parent equation, the idea is we want the parent equation to be a function of a single variable if possible. We're going to run up against an issue today with a problem where we've got to deal with something, with an issue there in that step, and that's important to know how to do. We come up with this parent equation, and then we implicitly differentiate that to kind of make it dynamic, right? We're going to calculusify it, and we're going to introduce the rates by differentiating with respect to t. And then that static parent equation becomes a related rate equation. And that's what allows us to solve for whichever rate we're trying to find. And then step 4 is just algebra, just plug and chug. Isolate whatever we're trying to find in that equation and plug in values and get an answer, okay? So we looked at one example yesterday. Let's look at this one today. This is a good one. So here's the picture that comes with it. A television camera at ground level is filming the liftoff of a space shuttle that is rising vertically according to the position equation. S, which is like vertical position, vertical height, equals 50t squared. So they're giving us a kinematics equation, right? Where S is measured in feet and t is measured in seconds. The camera is 2,000 feet away from the launch pad. Okay, so there's a bunch of information. It says, find the rate of change in the angle of elevation. What's the angle of elevation here? Yeah, it's theta, isn't it, right? So that's the angle between, when you talk about an angle of elevation in physics, you're talking about the angle between horizontal and the object, right? So there's our angle of elevation, theta. We're trying to find the rate of change in the angle of elevation at 10 seconds after liftoff. So there's the index on our video that we're watching. We're looking for the frame at 10 seconds, okay? So we already have a picture that's already made for us, right? Where we have theta, we have 2,000, and we have S. And if we had to solve for the hypotenuse for some reason, this is a right triangle, so we could solve for the hypotenuse, square root of S squared plus 4,000. Okay, is that right? That's not right. 4,000. Where did we get 4,000? 2,000 squared is a lot more than 4,000. That's not quite right, is it? It's going to be a lot bigger than that. It's going to be 4 million, right? Square root of S squared plus 4 million. Anyway, what do we know? And what are we trying to find? They tell us t is 10. Okay, we're trying to find theta dot, right? Okay, theta dot is that's the missing piece that we're trying to find. So let's write that down. That's what we're trying to find. Okay, what can we find? What else do we know? Okay, now that's something we don't have to write down because that's a constant. Okay, what we want to do is we want to write down the instantaneous values of the things that are changing. Go ahead, and you got something, Anson?
How do we know the yellow? Like the yellow.
How do we know that?
Yeah.
I'm just going to erase that. Well, that's something we would know because it's just Pythagorean theorem.
Oh.
Okay, but it's not right anyway, so I'm going to erase it. That's all the stuff we're initially given, right? And then we can set up a trig function based on the two sides that we know. What else can we calculate? At t equals 10, there's another quantity we can calculate. S, yeah, right? S of 10 would just be 50 times 10 squared. So what is that, 5,000? So we know S equals 5,000, right? And we could even do something else. If we know, look at this function we have here. We know that S is equal to 50 t squared. So could we come up with S dot? How would we calculate S dot? Yeah, just differentiate S with respect to t, right? So S dot, and this is really S of t, right? And S dot of t then? What is S dot as a function of time? 100t, yeah. Okay, does that make sense? And it makes sense that S, the speed, because S dot is really just vertical velocity, isn't it? If S is vertical position, S dot would be vertical velocity, right? The vertical velocity is increasing. Well, that makes sense for a rocket. It's increasing speed as the rocket engines fire, right? Okay, so at t equals 10, what is S dot? Yeah, 1,000, right? So we know a bunch of stuff. We know S dot equals 1,000, S equals 5,000, and we're looking for theta dot, right? Okay, we have a bunch of stuff, and maybe we can even add more later if we need to. Okay, so now what? Parent equation. We need an equation that relates S's and thetas. We already have it, don't we? Right? It's right there. There's and you can tell if we're trying to get an equation that relates angles and distances, it has to be a trig equation, right? It has to be like a right triangle trig equation, okay? So we've got our parent equation. It's right here, tangent theta equals S over 2,000. What do we do with our parent equation? Yeah, we implicitly differentiate with respect to time because we need to get dots out of this, right? We want rates of change with respect to t. Okay, so what happens if we implicitly differentiate this with respect to t? What are we going to get, right? So what's the derivative of tangent theta with respect to time? What's the derivative of tangent? Secant squared, yeah. So secant squared theta times theta dot, there you go, times theta dot equals, well, what's the derivative of S over 2,000? That's just like 1/2000th times S, right? What's the 1/2000th just stays put. That's a constant. What's the derivative of S with respect to t? S dot, yeah. Right? Okay, does that make sense? Okay, good. Good, good. All right, so now we got to solve for theta dot, right? Okay. So what do I do? Isolate theta dot. So what's that mean I need to do to get theta dot by itself? Okay, but secant squared is really just, in terms of sines and cosines, is what? Okay, so we could even rewrite this if we wanted to as theta dot over cosine squared theta equals S dot over 2,000, right? Does that make sense? Okay. And then I could multiply each side by cosine squared and get theta dot equals S dot over 2,000 times cosine squared theta, right? Okay, so I know S dot, but I don't know theta. So what are my options here? Okay, I could. There's a couple things I could do. One thing I could do is I could go back up to my video frame value list, right? That kind of that snapshot list, and for step 1, and I could solve for theta, right? I know that at this snapshot in time, at t equals 10, that's what the triangle looks like, isn't it? Didn't we say that the value of S was 5,000, and we know that's a constant 2,000, and so we could figure out what the hypotenuse is, right? That make sense? By Pythagorean theorem. So it's just going to be the square root of 2,000 squared plus 5,000 squared, which is what? I mean, what's that going to be? 25. So that's going to be like 29, square root of 29 million. Well, I don't know what that is, but square root of 29 million.
Yeah, that's actually a little number.
Okay, let's figure that out. So a million would be 1,000. So that's going to be square root of 29 times 1,000, whatever that is, right? Okay. And so now we've got all three sides of that right triangle. And so one thing I could do is I could literally write down what theta is. I don't even need that to find theta. Theta is the arctangent of 5 halves. Anybody see that? Because look, if I solve theta, if I use this relationship, if tangent theta equals 5 halves, 5,000 over 2,000, then theta equals arctangent of 5 halves. Okay, make sense? Yeah. Everybody see that? Okay. So that's one thing I could do, and then I could just plug, because that's just a calculator number, and then I plug that into my answer wherever I have a theta, right? What would that look like on a calculator? It would just look like, well, here, let's just calculate that on Desmos. Cosine squared means cosine theta squared, right? So it would look, actually, let's just write it out. It would look like this. So this would equal S dot, which was 1,000, right? Yeah. It's just that. Those are just a bunch of buttons you push on a calculator, right? Everybody see that? The arctangent of 5 halves is feeding us an angle that goes into the cosine function, and then we square that result because we have cosine squared. And that just gives us a number, right? Okay, the other thing we could do, I have a personal preference here. I kind of like using a reference triangle instead. And so if we have a cosine of theta, well, what's cosine of theta? Cosine of theta in this triangle up here, cosine is just adjacent over hypotenuse, right? Everybody see that? So then I could replace this cosine theta. I could just replace that with, what was it again? It was 2,000 over square root of 29 times 1,000, right? That's cosine theta, and then I just have to square that, right? Well, look, those cancel. So I get 2 over the square root of 29 squared. Isn't that just 4 over 29? Okay. So then we just get theta dot equals 1,000 over 2,000 times 4/29, which is just 2 over 29. So that's theta dot. That's an exact answer, right? I mean, you see what I did there? I mean, everybody gets how we got that cosine from the reference triangle. That's just opposite over hypotenuse, or adjacent over hypotenuse in our reference triangle, squared, right? Okay, what would the units be if we're calculating theta dot? It tells us we're measuring time in seconds. So degrees per second? That sound good? Degrees per second? Okay, but what if Jim Degree had broken up the circle into 3,600 degrees instead of 360? Back whenever he invented the degree. See the problem? Well, because we never once referenced a degree in this whole problem. And so if we express our answer in degrees per second, we're at the mercy of whatever Jim Degree decided a degree was going to be. That's an arbitrary measurement, right? So if we went back in time and old Jim had divided up the circle into more or fewer degrees, that's going to somehow change the result of this. That can't happen, right? So degrees must not work here. What would it have to be, do you think? It's got to be radians, right? Because radians are that's the only angle measurement that has an actual meaning, right? Radians are intrinsic, degrees are arbitrary. Make sense? Okay, yeah. So moral of the story. Whenever you're mixing linear units and angular units and you have to write an angular answer, you can't use degrees, right? You can only use degrees if the whole problem is defined in terms of degrees, right? Which we haven't done here, okay? So we'd get 2/29. I hope that's right. Oh, here's the answers. Let's see. Well, there it is. Oops. Yeah, there it is as a, 2/29. We're good. Yep. I'll put this down here for our notes. Come on. Okay, how do we do on that? Any questions? That sort of kind of maybe taking form a little bit, how we're doing that stuff? Okay. And remember, so I will point out one important thing was, like, we were able to go back and calculate things and add them to this snapshot value list, right? We can go like use that triangle, that reference triangle, and go back and just make other calculations for specific values that are happening at t equals 10. As we calculate them, we can plug them into that list. Okay, how about one like this? Find the rate of change of the distance between the origin and a moving point on the graph of this parabola, y equals x squared plus 1. So we've got this wire bent in the form of a parabola, and this bead is just sliding along the wire, right? And we want to know what's the rate of change of the distance between the origin and that bead as the bead slides along, such that dx dt equals 2 centimeters per second. So what does that mean? Derivative of x with respect to t. Okay, but what does that mean in terms of the bead? If dx dt equals 2 centimeters per second, what's that mean about the motion of the bead? Okay, say it again. Okay, so it's moving horizontally at a speed of 2 centimeters per second, right? So the x coordinate of that bead as it moves along is increasing at a constant 2 centimeters per second. Okay, does that make sense? So seen from above, if you're staring down at this bead moving on the wire, you would see the bead moving to the left or depending how you're looking at it. I mean, it's moving to the right, but if we're looking straight down on this thing, it's moving in that direction at 2 centimeters per second. To accomplish that, it looks like it's probably going to have to start going pretty fast when this parabola gets steep, right? Does that make sense? If x is going to continually increase at 2 centimeters per second, it's going to start to have to cover a lot of ground vertically to keep up with that horizontal pace probably, right? Okay, so what are we trying to find here? I guess we need to assign a variable to that, right? Let's call that S. How about? S will be the distance of the bead from the origin, right? So then what are we trying to find? You know what? I think we have to assign a time here too, don't we? Yeah, let's say I think I need one more piece of information here. Let's do this. Let's say when y equals 5. Okay. Actually, let's do better than that. Let's say hang on, I got to do a little calculation here. I'm going to say when x equals 5. We'll do that, okay? So when x has gotten out to x equals 5, we want to know how fast is the bead moving along on the wire, okay? So what's the stuff that we know? Well, we know x dot equals 2, x equals 5, and what are we trying to find? S dot, right? We want to know the rate of change that the bead is moving away from the origin. Okay, give me 1 to 5 on that. Does that make sense? Okay, ask some questions. Yes? The dot, okay, so, you weren't here today, were you? So dot is the special notation we give to a derivative with respect to time. It's like a prime. Remember how we'd say y prime, like dy dx, we'd represent with y prime? dy dt, we'd represent with y dot, because time derivatives are so special because they're, applications of systems like this are always evolving with time. We want to be able to recognize when we're differentiating with respect to t, so we put a dot instead of a prime. That's all that means, yep. Okay? Okay, so yeah, I bet that was a little bit strange. Okay, other questions? Okay, so now we need a parent equation.
How do you know x dot is 2? Is it different than x dt?
Tells us that right there. Right, dx dt is x dot.
Well, also, isn't it that's a derivative of okay? I mean, like, if you have a derivative of y.
That would give us y dot, wouldn't it? Yeah, okay. So one thing that might be useful is, how about this triangle right here? That's a right triangle, isn't it? What are the coordinates of that point? X. Well, I mean, what are the coordinates right there of that point? Right there? X, Y, aren't they?
What?
It's because we just don't know.
I mean, we don't, right there, we don't know what they are. They're changing, aren't they? Does that make sense?
Yes.
Okay. So x is changing, y is changing, but we've got these two variables, x and y, that represent the position of that point, right? So this is x, and that's y. And where's s? Yeah, that's the distance between the point on the parabola and the origin, right? So this is s. Okay, look, all the stuff we're given up here involves x's and y's and s's, right? So what's our parent equation going to be then? What do you think? Yeah, right? X squared plus y squared equals s squared is our parent equation. Right? Everybody see that? Okay. Okay. So go ahead, question? So the parent equation is the static equation. If we ignore all the dots up here, we want to be able to relate all those variables. So now when I differentiate with respect to t, that parent equation will turn into a related rates equation because we'll have rates in it, right? And we're trying to find s dot. Well, how are we going to get s dot? By differentiating this equation. Okay, but I want you to just, now here's where I want you to anticipate some problems. If we just differentiate that with respect to t, I'm going to get what kinds of things involved in my equation? Well, actually, let's just do it real quick. If we differentiate with respect to t, doesn't that just give me 2x x dot plus 2y y dot equals 2s s dot? Okay, that's a lot of stuff that we have to plug in there, right? What do we know?
And we can use that equation to find y.
Okay, we have x and x dot. We know y in terms of x, so we could go through and probably find y dot and plug in values for x and find y, couldn't we? Okay, we could. What's another option? What do you think?
So we know x is 5 and we know that y is x squared plus 1. Can't we just plug it in as it is and solve for s?
We could, right? We could plug that value in up here and find a value for y. And we could find y dot, and then y dot's going to have x dots and x's in it, so we could plug that stuff in and find y dot, couldn't we? That would all work, but there's a better option here. What's the simpler option? Do I have to have, let's not do this green derivative yet. Could we do something to the parent equation to make it easier? Say it again. What?
Or just solve for s?
Well, I mean, I could square root to solve for s, but then I introduce a radical, and those are ugly derivatives, aren't they? Right? That's not it. But is there a way I could eliminate a variable here? Okay, so this is kind of the trick we're looking for. So when we've got this parent equation that involves the independent variables x and y, and then the dependent variable s, right? S is what we're sort of calculating. What do you think?
Did you replace y with x squared plus 1?
Exactly, right? Exactly. This is a secondary equation. Here's a separate equation that relates only the x's and the y's. If I have an equation that relates x and y, I could solve that for either x or y to do a substitution, couldn't I? It's already solved for y. See what I'm saying? So look at this. We could just make a substitution right there. And then that's going to give me only x's and s's in my parent equation, which is way better. When I differentiate, then I don't have so many different kinds of values to plug in. You see the benefit there? So if we have that, if we've got some parent equation that involves more than two input values, then if I can just find a way, a different equation that relates those so I can make a substitution and eliminate a variable, that's always a really good idea. Makes things simpler, okay? So yeah, so let's do that. Let's combine those things. So if we go down then, if we take this equation, x squared plus y squared, well look what y is. Y is the quantity x squared plus 1 squared. That equals s squared. Okay, that's going to be way better. Now we've got x squared plus, square that out for me, x squared plus 1 quantity squared. What is that? Good, so if we combine like terms, then we just get x to the 4th plus 3x squared plus 1 equals s squared. Okay, way better. Now if I implicitly differentiate with respect to t, what am I going to get? So 4x to the 3rd x dot plus so we could divide each side by 2 and factor out an x dot, right? And then I just get 2x cubed plus 3x x dot equals s dot, right? Make sense? Okay, now we're getting somewhere. Now I could solve for s dot. So s dot just equals 2x cubed plus 3x x dot divided by s. But what's s? S is really just from this equation right here. S is really just the square root of all that stuff, right? Does that make sense? So I don't even have to calculate s in my list. I can write s in terms of x's, which I already know. X is 5, isn't it? Yeah. At our snapshot, right? Okay, remember, and that's just s. Okay, and now I can just plug and chug because we know x dot is 2 and x is 5, and those are the only ingredients of that function now, right? So if we plug all that stuff in, what do we get? 2 times 5 cubed, so that's 250 plus 15 over, yikes, what's this going to give us? Square root of 625 plus 75, so 701, I guess. Times x dot, and we said x dot was 2. So somebody crank that out, put that in a calculator and see what we get. It's on a Desmos or something, yeah, or calculator. What did we get? 265. So what is that? 500 divided by. Okay, 20.01, that sounds about right. Something like that, 20.01-ish, right? And units would just be centimeters per second, right? Okay. Why so fast? Well, because it's pretty steep there. It's having to go up a long ways now to move horizontally, right? You have to go up pretty fast. Does that make sense? Okay. Give me 1 to 5 on that one. How we doing? Okay. Okay. Just go back, kind of just scan through it here and see if you can ask a question to help me clarify something for you. What part is the least clear on that process?
Why can't we plug in 5 for X?
You can. You can. So an alternative would have been, you could have plugged, you mean like plug to get Y, you mean? Is that what you're saying? Yeah, so we could have just plugged in X equals 5 and gotten Y equals 26, right? The only issue there, I mean, it would work, but then we'd have to calculate Y dot also, because we would have had a Y dot. So if we did that, Y dot would be 2X, X dot, right? So we could do that. I mean, 2 times X would be 2 times 5 is 10 times X dot. So we just would have gotten Y dot as 20, and that would have worked too, right? We could have just added those to the list and used this function right here, right? And gotten the same answer. It would have worked. Okay. Just in general, though, it's nice for us to try to do the calculus in terms of as few variables as possible. Okay.
Because we already have the X dot, that's why you wanted to do that.
Right, because we had information about X and we were given only information about X. It was more convenient for us to try to write this with X's only. Yeah, exactly. Yep.
So why couldn't you just put X and Y in the parent equation? And then add that.
Well, we did have X and Y in the parent equation originally.
Like for 5 and 26, like 5 squared plus 26 squared equals S squared.
You could. To find S? Yeah, we could have. And then we could have added S to the list also. Right? We could have done all that. That's fine. It all would have worked. What we did instead was we just wrote this whole thing in terms of X's. So all we had to do was plug in X and X dot. So essentially, the calculations we would have done are just buried in this expression right here. Does that make sense? Right? Okay, but I don't think we made it harder, because I'll show you an example of where, like, the next one will be like this guy. Okay, this is, I don't know, we're not going to get through this, but here's an example of one where we're going to have similar options, and it is so much easier if you eliminate a variable. I mean, it really makes this problem a lot simpler. So let's at least think about this a little bit here. Just get a strategy going, and then we'll deal with this next week. So at a sand and gravel plant, sand is falling off a conveyor onto a conical pile at a rate of 10 cubic feet per minute. So what is that, by the way? What quantity is that giving us? 10 cubic feet per minute. V? Is it V? It's not V. Cubic feet per minute? 10 cubic feet would be a volume, but it's not just giving it, it's giving us what? A rate. Yeah, so what is that? It's not V, it's V dot. It's a rate of change of V, right? Okay. It says the diameter of the base of the cone is approximately 3 times the altitude. At what rate is the height of the pile changing when the pile is 15 feet high? So you can already see that the parent equation here is going to be the volume equation for a right circular cone. Right? This is going to be, that's going to be the parent equation. Okay. How many variables are we doing? I mean, like, V is a function of 2 variables, R and H there, right? So if I do this derivative, that's going to be kind of a pain. I'm going to have to do a product rule there. Does that sound fun? Right? Because I've got 2 different variables. I've got R's and H's. And so I'm going to have to do a product rule. My derivative is going to involve R's and H's and R dots and H dots. That doesn't sound very fun, right? So it would be much preferable if we could somehow eliminate one of those variables, right? Okay, all we need to eliminate a variable is a secondary equation. We need some equation that relates the r and the h, so I could solve for, we're trying to keep the h's, aren't we? We have information about height. So we'd want to be able to solve for r in terms of h and substitute in that equation. So I can get rid of the r's in favor of h's. Do you see that concept, right? I just need, that's something I really want to do. Do I have some information that allows me to do that?
It says that the diameter is 3 times the altitude and the radius is just half the diameter.
That's it, exactly. Look at this. That's what gives us the extra information that allows us to make this problem much simpler. The base of the cone is approximately 3 times the altitude. Okay, so then that means that 2r is the base, right? 2r is 3 times the altitude. Does that make sense? So we have a picture. It's easier to see in a picture. So here's a picture, right? There's the diameter. There's the altitude, y, okay, or h, I guess it would be. And so we just want to come up with an equation that allows us to only write this in terms of h's, right? Okay, so what's that mean then? Let's rewrite that statement. The base, so 2r is 3 times the altitude, 3h. Agreed? Diameter equals 3h. So we want to eliminate r, so all we would do is solve for r in terms of h. R equals 3/2 h, and let's plug that in right there. And then I'm going to have volume as a function of h only, and so this is going to be a much easier derivative to do. It's not going to be product rule. See the benefit there?
Do we plug in 15 for each also, or just?
Okay, so now can we plug 15 in now? No, because 15, that's the value at that one frame in the video, but h is changing, right? So if I plug in 15, it's going to look like it's a constant, and the derivative would just be 0, right? Yep.
Do we need to worry about the word approximately, or is that?
No, that's fine. Yeah, no, they're saying, they're telling us that we can make that, we can assume that relationship. Yeah. Okay. So then that allows us to change this to where the parent equation becomes next week. Okay. Yes.
I'm gonna go talk to Clem, and then I'll.
Okay.